So it's really important, again, you don't know this, but I'm recording just now, okay, where we're going and where we've been, and it's really important we connect those two dots. So we left off last week finishing a lab, and we collected a gas by water displacement. And we connected all concepts in the gas law lab. So the whole idea last week was to figure out exactly what the molecular mass was, okay, of this butane that we collected by water displacement. Now, water displacement is a great way, okay, it was butane, not propane. It was a great way for us to collect gases, but only if what? Those gases do not react with the water or dissolve in the water, okay? Because if they do, then we wouldn't collect the gas appropriately. So it's a great way to fill this tube up, collect the gas. But our problem is that when we collect the gas by water, what do we have? In the
Water vapor.
We have water vapor and the gas. So we had to subtract that away, okay? And so that's key here. The key here is that we had this and we had water vapor. And so in order to do this, we figured out the total pressure by the manometer problem, all right? We know that the atmospheric pressure was pushing down, which is really pushing this liquid and supporting this column up. And we know that the gas pressures are pushing down. Who's winning? Atmospheric pressure, okay, was winning by that much. And because of the story of Torricelli, you know that supporting a liquid, okay, in a column is where the first barometer came from. Now this is the water. We have to do what? Convert it to mercury. And so we did all of those things. I'm not going to review the entire lab, but the point was, the key to the lab was the total pressure in this flask was equal to the individual pressures. Dalton's law, okay? And the key was that we had to subtract out the water vapor. Water is continuously evaporating. Did it bother anyone that we took a table and just used the tablature of the temperature and then we used it? Did that bother anybody? Yeah, it felt like we had all this work that we did and we just used just a table, okay? And we're able to do that for reasons I want to make sure I review today. Why did I take a temperature in a table? I feel like we learned about gas laws. Volume is proportionate to temperature. Volume is proportionate to 1 over. Volume is proportionate to n. We have all these interconnecting variables that I made you go over in that test, or that derivation. Yet, I just give you its temperature, and we get a vapor pressure of water. A gas of water. That bothered some people, I know it did. We did all this work, and here's a table. I just gave you a table, and you used it. Why can we do that? All right, so that's where we're headed today. Where we're going to go is also talk about why we can use that temperature and what it relates to the next piece of this unit. Okay, this last little piece of unit this week is showing where all the errors in gas laws come from. We've done 2 labs, we're going to do 1 more lab. You're holding on to them because we're going to write a simple conclusion that talks about the errors in all gas law labs. What's that? There's really one major one. There's always errors in the experiment. You can't make a perfect experiment, okay? There's always some inherent errors, but there's one major error in all gas laws that you have to understand, okay? And it's tied to the fact that we can read a temperature and get a vapor pressure of water. Not that water is in every problem, but it's tied to that concept. So this weekend I made you do what? Do a form, and you guys with two or more what? Submissions, you guys definitely rocked it. Okay, so I want to pull that up. Okay, and go over just kind of one question really. I emailed everybody their score. I emailed everyone the key, and I just want to go over really one question because only one question that you guys got incorrect as a group. All right, so the most of these were 100%. Okay, and to be honest, parts of this is Regents level, but parts of this is connected to the AP level. So this is the question. Almost all the other questions averaged 97 to 96%. So you guys did an awesome job taking that lecture, reading the notes, okay, using each other appropriately, and coming up with an answer. But this is the one where it was like 71%. Everyone else was like 97 to 100%. Okay, so what is this right here? Okay, this is a very important graph called a Boltzmann distribution graph. And Ludwig Boltzmann, funny thing about him, it's not funny, he came up with these curves saying how random water was. how random water vapor or how random gases are. He was the first really scientist to truly believe that atoms exist and particles existed. And because of his particle theory, he came up with these distribution graphs. He actually came up with the first constants that we used, engineers used to build steam engines. Okay? Remember, we didn't accept atoms until 1905. Atoms were not accepted scientifically. Well, we were building steam engines way before then. How does steam engines work? Okay? Very simply, think about a locomotive. Choo-choo! This is a terrible choo-choo, but how a choo-choo works, or a locomotive, and I'm not drawing a really good one here, but what they have is they have, of course, wheels, okay? And tied to this wheel, okay, is a piston. I don't know if you ever watched, okay? But essentially, you've got a piston, all right? And if you ever watched again, the best way to draw this would be a circle, okay, here, because they have a boiler, okay, which they basically put a lot of water in. And that boiler creates steam. And what does this steam do? Oops, gotta go this way, okay? Okay, so steam, so they boil water. So if you've ever seen a locomotive, what do they do in the car next to it? They have either wood or coal. They keep throwing coal onto a fire. That fire keeps taking the water and boils it under pressure. That pressure goes into, and if you look at a picture of a locomotive, a steam engine, there's an actual syringe, okay, if you think about it, okay, right at the end. And so it starts this way. Okay, I gotta take the end off. All right, and so they put in the steam. What do you think happens? Expands. You put in more gas molecules, it bounces in all directions and pushes this forward. And of course, this is tied to the wheel a little bit, and it makes the wheel go what? Forward. Okay, then it gets cools again, and here we go again. So this piston going back and forth is just putting particles. His equation allowed the scientists of the time to build steam engines. Yet, so the engineers knew that particles existed. Okay, unfortunately, he committed suicide in 1905 because it wasn't accepted. None of his work was accepted in the scientific community, even though engineers were using it, because no one believed in atoms. 2 months later, Einstein, with his equations that we'll talk about later, mathematically proved atoms existed. But these Boltzmann distribution curves are absolutely important. He was the one who first thought about that particles move, not randomly, but with some organization, like we talked about in EP Bio. Okay, we talked about EP Bio with a normal distribution. So let me talk about this for a second because it's everything that we're connected here to. So a Boltzmann distribution graph says that a gas, okay, these are number of particles, number of N, as we talked about, moles, number of gas particles. And if we're at a particular temperature, there's a range of speeds these gases have. Okay, so this could be at 40 degrees Celsius. They're not all going at the same speed. If you think about a billiard table, right? Have you ever played billiards or pool? If it's cold, I don't know if you guys call it something different. Does anyone play that game anymore? Okay, no? All right, well, when you have a ball, a cue ball, hitting a bunch of other balls, if you're gonna break, okay, some go faster, some go slower. If you think about particles moving, hey, 2 particles could collide into one, and this one's gonna go much faster. Or what? 1 particle could hit another particle, but then another particle can hit another and could slow it down. You're gonna have a range of motion. Okay, if you think of your head, and I want you to think about particles moving randomly. Okay, some are gonna go faster, some are gonna go slower. But there's gonna be more particles around the average. That's what a normal distribution is. Okay, so there's your average. Okay, so there's some speed at which, and we'll talk about that speed this week. We're gonna actually calculate that. It's an average speed that they have at a particular temperature. Now, here's the key with Boltzmann. Okay, the key with him was he understood that speed, of course, is kinetic energy. Energy of motion. And we also know that these particles do attract each other. This weekend it was about intermolecular forces of attraction. How well do particles stick together? I've had these things up here forever, okay? And so if I had 2 water molecules, all right, and these are gonna be extremely big under this thing, but there's a water molecule, oxygen and hydrogen, okay? And it's gonna attract another, okay, oxygen. Now, the magnets are gonna stick, okay? But if I was to make this smaller, This is showing the hydrogen bonding between water. So these are what we call intermolecular forces of attraction. The H plus, which we learned already is hydrogen deficient, is going to attract the negative part. Now, of course, they're touching, they look like they're bonds, but these are molecules attracting, okay? And when we talk about this work of vapor pressure, we're talking about the ability of water to overcome these attractions. I can draw it a little differently. So here's an oxygen. We'll learn why it's bent. Okay, here's the molecule, kind of drawing it representatively. Okay, here is another water molecule. I circle them to show you the two distinct individual particles. But this is a positive end, okay? And the reasoning is that oxygen shares this pair of electrons really closely, so kind of hydrogen lost it. We'll talk more about that. The oxygen end, because it pulls this pair of electrons closer, has electron-rich area, is negative. So there's where the attractive force exists. Here we have them touching because they're magnets, but they stick together by what we call H bonds. And there's a bunch of different intermolecular forces of attractions, IMFs. They are not bonds. They're not strong as bonds, but they still need to be overcome. Any case, here's what Boltzmann said. Okay, very important. And it was part of your homework, but this is where you guys did the worst as a group. So, and this is probably by far one of the most important pieces to our AP understanding. So, if I draw a line in the sand, that if molecules, any molecules that have any energy above, if they're faster, okay, let's just say there's always this line in the sand, this threshold by which if you have a high enough kinetic energy, you can overcome those attractive forces. Let's pretend it's water. Okay, but if you notice something, that doesn't mean every single molecule, let's say, of water, liquid, okay, or gas can overcome those attractive forces. Only the ones that are what? Faster can overcome. So there's only a small fraction that have a high enough motion kinetic energy that can overcome these small, weak, attractive forces compared to bonds. And when they do that, they become a gas. Okay? So when I'm talking about molecular motion of gases and or liquids, I can use the same graph. I could say, here's the motion of water liquid, here's the water of motion gas. But let's say this is H2O liquid right now. And these are all the range of motion at 40 degrees Celsius. Okay, what do I know? There is some fraction of them that have enough energy to overcome their attractive forces and they evaporate. See, people think that evaporation is boiling. We're going to make sure we understand the differences there. But we know that evaporation occurs when water is warm and when it's cold out. We have puddles outside, if it's cold out, they evaporate. They evaporate a little slower. Ooh, slower. Okay, temperature just equals air pressure. On a warm summer day, they evaporate faster, but they're still evaporating. Okay, let's go 50 degrees Celsius. Okay, what happens? At 50 degrees Celsius, hey, the same are particles, the area is the same, but this shifts. This shifts, okay, and I'm going to draw it this color. It shifts and flattens out. So what happens here? So when that flattens out, what do we know? We don't need those guys anymore. So now that it flattens out, isn't there more molecules above that threshold? So at higher temperatures, isn't there going to be more vapor pressure of water leaving? Of course. So this is going to flatten out. So as temperature increases, this guy pushes forward. What happened to the average? If this was the average temperature or the average speed, what happened to the average as temperature went up?
To the right.
Yeah, it went to the right. There are more molecules on average going faster, which means there's going to be more of them that can what? Overtake this threshold, which means that more of them can overcome that attractive force, more of them can evaporate. So temperature is only a factor in vapor pressure. And don't forget, vapor pressure is nothing more than the force of liquid molecules doing what? Evaporating. I'll draw this until the cows come home. These little circles are water molecules, ethanol molecules, particles. They attract each other. But some of them have enough energy, not all of them, some of them, and if they get to the surface and overcome the attractive forces, they evaporate. And that force upward we call vapor pressure. And if I apply more energy, hey, that distribution shifts to the right, and more of them evaporate. So how much gas we get from liquids evaporating is only due to temperature. There's no other factor. No other factor. There's nothing in playing. Basically, we're saying, hey, there's a force of attraction. You give me more motion, I can overcome it. Okay? There's no opposing forces, nothing. That's why I can give you a table. Okay? So gosh darn important there. Okay? Now, where does this lead us to where we're headed? Because we know that water molecules attract each other. We've been pretending forever that gases don't attract each other, independent particles. But we're going to find that gases as particles attract each other. And that's going to lead us to our errors, and that's where we're talking the rest of the week. But I want to continue on this path. Now, something else I want to mention when we talk about Boltzmann distribution graph, okay, is that what if I compare two different liquids? That's what was for homework as well. Here I have water at a certain temperature, okay, and let's have propanone. Propanone. What's the difference there? These both are at the same temperature. This is water, and this is propanone. What's the difference? What's the difference? Somebody home, what's the difference? Oh, why that's so blue.
Molecules escape in propanone then.
The molecules escape in propanone easier?
Yeah.
Okay, so another way of saying that is that it has what kind of vapor pressure? Higher at the same temperature, correct. And how do I know that? If this is the line in the sand, clearly there is more what? Molecules of propanone that can escape the threshold at the same temperature. Hey, that evaporates faster due to what kind of attractive forces? If I can leave the liquid phase easier, weaker. Okay? So if propanone can escape each other's particles easier, it's going to deliver a higher pressure upward. So weaker forces of attraction between the particles lead to liquids having greater evaporation for the same temperature or higher vapor pressure. Important. Good stuff there. All right, and that's important. All right, now let's get back to, okay, some more connections here. Okay, all that was part of your weekend homework. Okay, and a lot of that lower level stuff is Regents level, but the connectivity that we have through AP, that's the bare bones as well. Okay, so let's be crazy and go through some of this again, okay? Before I do that, okay, I got this photo in a recent Newsday article, okay? I'll read you the caption. It says, early morning fishermen on Lake Alexander near Motley, Minnesota with a flock of birds as the state's walleye and northern pike season opens Saturday. Yes! Temperatures dip below the freezing point, okay, causing the 50-degree lake to steam as the sun began to rise. Anything bother you in that statement? Now, Newsday is written for an 8th grade level. English, they break any science based on what I told you there. So I'll read the part where I think there's a problem. Yeah, temperatures dip below the freezing point in the air, causing the 50-degree lake to steam.
The word steam.
The word steam. Steam means what?
So like heat.
Like
Means
boiling.
vapor, water vapor, correct? So only when the temperature dropped below what freezing, did the lake start to steam. If that's the case, water, we don't have a threshold. Water doesn't evaporate because evaporation is steam, right? Okay, well, let me help you something. This fog you see is not steam, it's liquid particles, it's fog. Ever drive through fog? Your folks or yourself have to turn on the windshield wipers. What's fog? So as the temperature dropped at 50 degrees, probably Fahrenheit, the water was still evaporating, causing steam. Steam's in here. You can't see steam. Water vapor you cannot see. If we could, we couldn't see each other. You're doing this, okay? So you can't see steam. So think of what's happening. Water vapor, okay, this isn't the full time, so the lake is still warm, Okay, 50 degrees, okay, for Minnesota is pretty warm. Okay, I wouldn't go swimming in that. It's Fahrenheit. So it's evaporating really well. Now, when the air temperature dropped, that gas going up, that water vapor went from a gas to a liquid called a condensation. And when it condensed, it made a small little particle, fog. Okay? So you're not seeing steam, you're seeing it was a foggy morning because the vapor pressure that continuously leaves the lake, okay, at this point, hit very cold air and condensed back into a liquid. The idea here is that steam only occurs when you boil something. No, no, no. Water is continually evaporating. Even at cold temperatures. Even at cold temperatures, we move this thing back. There's still going to be what? Not as much, but still some molecules that have the kinetic energy to overcome their attractive forces, even at zero. So let's talk about that. So I just love to look at those things. So 8th grade reading, but I'm not sure what the science was. Again, we'll talk about that in a second, but the visual is very important here. Okay? When I talk about vapor pressure,
molecules of a
forget the
liquid have a
voiceover.
range of kinetic energies. Some have enough energy to overcome intermolecular.
Forget the voiceover. But what's happening is, hey, notice they're not all going the same speed. And the ones that are faster can overcome the attractive forces, get to the surface, and leave. I know it's very basic, but that's the visual you have to have when you go through this course. Another great visual, okay? And I love this one. I know where it came from. Okay, but here are water molecules, okay? And they're attracting each other. Notice the positive attracting the negative, okay? And then all of a sudden we get to the surface. It's not a great video, but oh, some left. Not all of them, just some. But some that are at the surface and have high enough kinetic energy. Positive attracting, oh! Okay, so there is your evaporation that's occurring at some temperature. Okay, what's boiling? We'll get there, all right? Boiling is not just a place where it evaporates. Okay, so now when we measure vapor pressure, this is important, we measure it in equilibrium. Okay, this is very important. Okay, we talked about condensation in Lake Wale or whatever, the Wale season. So here is evaporation. Oh, but some are going to what? Condense. Okay, evaporation and condensation occurs at the same time in a closed system. Okay, that's how they measure. All right, moving forward. This is where I want to get to now. All right, very important. This is that table you got that people were bothered. Why can't I just use a table to get the vapor pressure? Well, watch. These are kilopascals. What's standard pressure in kilopascals? 101.3. So that reference table that we dealt with is 101.3. Okay, now, notice as temperature increases, what happens to the vapor pressure, the force of liquid molecules escaping? And of course, this thing shifts over and more molecules have that energy, correct? That's how it works. So if you have higher temperatures, you have higher energy to overcome attractive forces. Notice something, party people. When we reach 100 degrees Celsius, what is the pressure of the liquid coming up? Standard pressure. What? Well, remember Andy Celsius made his thermometer by marking his thermometer where the mercury rose and stopped. And then he made sure he was at sea level. It was important they realized something. Okay, so water was boiling at sea level. The reason why it's this way at 100 because we made it that way. But notice something at 0 degrees Celsius. Is there vapor pressure? Oh, that means ice is escaping into the gas phase. What do we call that? Sublimation. So, interesting enough, here's a question. Can I make water boil at 15 degrees Celsius? Yeah. Now, what's boiling? Boiling. Why did water boil at 100 degrees Celsius? Well, we made it that way, but standard pressure pushing down was 101.3. And that's a force due to molecules hitting a liquid. Don't forget, we deal with boiling. We have atmospheric particles slamming down in the liquid. So we've got this force. The pressure coming up, that's due to temperature breaking these what? Did I get it? Breaking these attractive forces. So temperature, vapor pressure, that's just due to breaking attractive forces. Nothing to do with the what? Opposing pressure of the atmosphere. But boiling, and I love to think about boiling, is a maximum evaporation. That's a place where you get maximum evaporation. That's the difference. What does that mean? It's a place we have the highest rate of evaporation. Why does that work? Because at some point, we start heating a liquid, its vapor pressure increases. Nothing affects vapor pressure except temperature. But the pressure, the opposing forces hitting the liquid are what keep it from reaching maximum evaporation. It's only when the vapor pressure upward equals the opposing slamming force of molecules hitting the liquid do we have maximum evaporation, called boiling. So this boils at 100 only when the pressure opposing is 101.3. If I increase the pressure, like in Death Valley, and why would Death Valley have an increase in pressure? Anyone know about Death Valley? It's the lowest, below sea level point on the for a country. I don't know if it's on the earth, but in terms of land. Okay, so that means you have what? A greater amount of air above you. So you have the highest pressure at Death Valley. So in Death Valley, with a higher pressure, with more pressure pushing down, guess what? You're going to need more vapor pressure pushing up. So you've got to increase the temperature to match that. So water boils at a higher temperature, okay, at that point. Now if I go on top of a mountain, hey, Denver, Colorado, been there once. I brought my thermometer, okay? I wanted to boil water. It's the mile-high city. I didn't do this. We went skiing with my friends in college. I didn't tell my friends, but I wanted to see what the water boiled at. Okay? Because I knew that I was elevated. Being elevated, I have what? Less pressure above me. The pressure drops. Okay, that's why when you climb Mount Everest, at some point you got to put an oxygen mask because the partial pressure of oxygen is too low. So if the pressure drops, hey, I don't need much pressure to what? So if the pressure drops, I don't need as much vapor pressure upward to match it. So we can make water boil at lower temperature. So when I ever ask you the boiling point of water, you can say, any number, theoretically. Boiling point is dependent upon the atmospheric pressure. The vapor pressure is always locked because it's about intermolecular forces. That's important. Any case in point, I boiled some water.
What temperature?
Okay, it boiled at 98. Now I don't know how good my thermometer was, but I was pretty happy that water was boiling at 98. Okay, so the idea that boiling even has to be hot is a silly thing too, right? I gave you a demonstration that I can't do right now because of the time constraints. But the liquid nitrogen in a can, you watch that demo?
Yeah.
Okay. Clearly vapor pressure. Liquid nitrogen, 80% of the air is nitrogen. How'd that happen? It already boiled. It's boiled at a what? Much lower temperature. So what kind of intermolecular forces of attraction do you think something that's a gas at room temperature compared to water, which is a liquid? What can you say about weaker or stronger?
Weaker.
So much weaker that it boils at negative 196 degrees Celsius. So I can make this go anywhere. And that's why when you say, what's the boiling point of any liquid, you can give me any number. That's why we need to say normal. I need to fix the atmosphere. So whenever I'm comparing liquids, I put the word normal. Okay, it's important. The normal means, hey, the pressure's locked. But if the pressure's 101.3, if I say standard pressure and say normal, I can ask you, hey, what's the normal pressure? Okay, or I can ask you, what is the vapor pressure of gasoline at its normal boiling point? Well, if it's normal, the atmospheric pressure is in kilopascals, 101.3, so what must be its vapor pressure? 101.3. I can ask you any liquid, okay? Cyclohexane, lighter fluid, okay? Lighter fluid. What would be its vapor pressure at its normal boiling point? 101.3 kilopascals, 14.7, and whatever you want to use, 1 atmosphere, okay? That's important. All right, now, it's hard to believe that, though. It's hard to believe you can change the boiling point. Boiling points depend on pressure, so I should do this for you, and I will. Okay, so here is the demo, where all I'm going to do is lower the pressure. The vapor pressure is going to be constant, so I'm dealing with water probably at 25 degrees Celsius. Is it evaporating? Yeah, not as high, and it's not creating a vapor pressure as great as boiling, but I'm going to lower the pressure above it, the opposing force, okay? So what I have is a pressure, okay? I have a pressure container, and that's a vacuum pump is attached. This vacuum pump is going to draw air out. When you draw air out, there's less what? Particles to slam down on the liquid. So I'm going to put this in. To show you how this works, what I have here is an accordion tube. Accordion tubes are used when you have liquids that easily react. This is accordion tube. Remember, I don't know if you guys anyone play accordion?
I
Mr.
used to have a
Booker,
toy
remember?
one.
It used to be cool until Mr. Booker took it up. Okay, now, I'm not sure if that's a cool instrument. All right, I want to learn guitar and accordion. All right, so in any case, accordion tube is a tube, okay, where either H2O2 decomposes into gases. So I buy it this way, but over time, it does that as opposed to the bottle what? Exploding. So in any case, what I'm going to do is I'm going to push it down, and there's air in here, but the air isn't what? It's pushing up. It's the same air on the outside, right? So what I'm going to do is I'm going to lower the pressure, take the molecules of gas away that are opposing, just like the opposing force of the atmosphere, okay? And all I expect to happen here is by taking the pressure away, taking the molecules out, what do we get? Hey, it's going up because the pressure inside is staying the same, just like the vapor pressure stays the same. It's the opposing force that's changing. So, relieve the pressure, okay? And there you go. So I'm going to lower the pressure. So I'm going to take water. Okay, it's water. It's no fancy chemical. Here we go. Okay, great. I can't drink. All right, now, so I'm going to put some water in here. All right. Now, this water is at room temperature, somewhere between 20 and 25 degrees Celsius. Okay, it's evaporating. Is it boiling? No, it hasn't reached maximum evaporation. What is the factor that affects its boiling point?
Pressure.
Hey, it's the pressure. So all I'm going to do, party people, is I'm going to, and for those at home, let's get up close and personal. And there we go. All right, now let's turn on the pump. Now all I'm going to do is take the opposing force. It has some vapor pressure going upward. All I'm going to do is lower the pressure enough so that it matches. When it matches, we have maximum evaporation. Here we go. Make sure I got a good seal. I think I do. Okay, lowering the pressure. At some point, the atmospheric pressure and the vapor pressure will meet. Okay? And we'll get some boiling. Maybe. Assuming I have, there we go. And we got water boiling. Now the question is, what temperature? So, now I don't know if you can see it, probably can't at home. Do you expect the temperature to increase or decrease here? Decrease, why?
Less pressure.
No, who's leaving? Who's leaving? Which air particles? Which air particles are leaving? Hey, I got something like this going on. Who's leaving? The higher speed, okay, molecules. Okay? Hey, if my highest GPA earning what? Students left. Okay? Kate, if you left, why are you laughing? Kate is as smart as anybody in here. If my highest GPA earners left this classroom, what happens to the average of the classroom? Right. So if my fastest moving molecules leave, doesn't the average speed drop?
Yeah.
Oh, it's energy drop. It gets cooler. Evaporation is an endothermic cooling process. The energy, it drops there. Okay, good enough. All right, now let's continue on because I got to go on to what this connection is. So that's everything we've learned. Okay, this is a great demo. I took the 4 liquids in the table and I swiped them, and we clearly saw who evaporated faster. Okay, now the boiling point for the last piece of this. The boiling point is what? These are the 4 liquids that I swiped. Who escaped? Who evaporated in front of our eyes? The propanone did because it had the highest vapor pressure, highest rate of evaporation. It was the first to hit atmospheric pressure. So its boiling point is the lowest. The temperature where its vapor pressure reaches is lower. The ones that have stronger intermolecular attractions boil at a lower temperature. Look at this curve. I want you to memorize this curve. It's unique for different liquids because every liquid has unique attractive forces. Only temperature affects evaporation. But the boiling point depends upon what this line is. Hey, water boils at what? 100. If the pressure is 101. But if I do what? increase that pressure, it'll boil at a higher temperature. That's what pressure cookers used to do. Growing up, we didn't have microwaves. We did have a microwave when I was like in middle school, and we looked at it like, whoa, what was that?
That's crazy.
We actually sat around at night watching it boil. 1 minute, ooh, water boiling. Okay? Good times. Okay? It's before you had YouTube video. I'm serious. It was like, whoa! Okay? And it had magical, we can cook chicken that was frozen. No, you couldn't, but we tried. Okay? All right, but the bottom line is, we can boil the water. So pressure cookers, you have higher pressure of the liquid. It made the water boil at higher temperatures. You cook food faster, but they were dangerous. Okay, they exploded. Okay, so probably your grandmother's, probably your probably mom and dad had a pressure cooker. Okay, so any case, we just did what? We lowered the pressure. Okay, so when comparing liquids, we need that. Okay, so what's today about? What's the next connection here? Okay, well, we already talked about all of this. Is look at that line. Look at those vapor pressure lines. Okay, we learned all of this during your form. I bring up SpongeBob because this is my favorite episode. Hello, I'm normal. How are you? Normal boiling point. Only when you're normal, okay, do you have a what? Fixed boiling point. Normal means you're at standard pressure. Love that episode. Hello, normal. Besides, I haven't figured out how do you light a fire under the water yet. And how do you have a beach under the water?
That's why Patrick lives under the rock.
Okay, everyone hopefully has not seen these, right? Because you don't use it anymore. Okay, the people that are using vape pens, they do this, but we used to use lighters. Okay, not that I smoked, I don't. Okay, because if I smoked, I'd have been much taller because it stunts your growth, right? But the point is, this is a lighter. Okay, and they still sell these, and these have butane that was in our what? In our lab. When I decrease the pressure, that's when what evaporation does what? It boils. So, Christmas in July. So, if I play this, okay, maybe. So when we press down, so there's liquid and gas here. Lower the what? Pressure. There's less, this pressure here is keeping the liquid from evaporating. If I lower the pressure, it evaporates more. That's how the butane came out when you guys pushed it out. Okay, so there's a connection. Moving forward. Okay, remember those vapor pressure curves? All right, let's go on to, we'll talk about the Alaskan pipeline. Let's talk about phase diagrams. Okay, there is your vapor pressure curve. Phase diagrams. Now, very quickly, a phase diagram outlines the pressure and temperature changes for the phase change. In boiling, okay, you have liquid to gas. Let me show you. Under higher pressure, low temperatures, what phase do you think you have? Where the highest pressure is pushing down on something, and they move, yes, that's just solid phase. Where you have higher temperatures, okay, where they're flying around as a gas, at low pressures on them.
Girl, if you fix the iPad.
Okay, what happened to it?
Just point it out, that's it.
Oh yeah, thanks.
The board.
Oh yes, okay, you getting bored? All right, sorry. Okay, my bad. All right, so here we go again. So when you look at a phase diagram, okay, we're talking about now how pressure and temperature can change the phase changes. Now this is a solid because you have the highest pressure, lowest temperature. Here you have the highest temperature, lowest pressure. That's a gas, in between's a liquid. Okay, it's called triple point. That's where all three can coexist. Okay, now, real quickly, when we go from one to the other, if I keep a constant pressure, stay with me, at a constant pressure, what's going to happen here? When I increase the temperature, I'm going to go from the solid to a what? Liquid. That point right there is melting. This way is freezing. Keep increasing that temperature under what? Constant pressure. I do what? Hey, okay, what if I have higher pressure? Won't I boil at a higher temperature? Okay, so this is a phase diagram. It's really cool. Now CO2. Now CO2 is sublimes. Okay, its triple point is 5. And let me explain this for a second. Okay, that means at 5 atmospheres of pressure, which is 5 times the pressure of us right now, we're under. If you increase the temperature, it goes directly from a solid to a what? To a gas. That's sublimation. Now the chill point part here for water is 0.0001. So 1 atmosphere for water is right here. So it goes from what? Solid to liquid to gas. Okay? Now think with me for a second. CO2 goes from solid to what? Gas, sublimes. What kind of air pressure does it have? It goes from a solid directly into a gas. Yeah, exactly. They call it dry ice for a reason. It doesn't become a what? It doesn't become a liquid. One little demo here. Nope. Okay. This dry ice we're not touching without a glove, but now what we can do with this is you can play a little ice hockey. Now, if you ever played ice hockey, and again, you probably haven't done that either, okay, because you guys are playing digital stuff, but if you crush these little pieces, okay, they kind of float. They float a little bit on the desk. Now, the reason why they float on the desk is why? Anyone know? Why does it float on the desk? Nope, not about density. What have I taught you all day? Why does this float on the desk? What's that?
Weak intermolecular forces.
Weak intermolecular forces. That leads to what?
Not attractive.
That leads to what? That leads to what? Hey, you haven't played ice hockey because you don't know. Ice hockey, Mr. Bookermer, what's pushing up on an ice hockey rink? Air. Not magic. Look at it. Look at it. It's floating around like it's ice hockey. Okay, now listen. Why it's floating is air is pushing up in an ice hockey rink. Why is this floating? Is because there are such weak attractive forces, the solid on the bottom is pushing CO2. This warm air is way above its sublimation point. It's pushing CO2 bubbles out to suspend it. Solids that have high vapor pressure, sublime. See you tomorrow.
What are we going to do with this?
Leave it right. It's going to sublime. It's going to go to gas. Leave the glove.
Is it cold?
It's kind of cold, but like
Don't touch it with your hand. Its sublimation point is negative 80. Okay? So it will cause frostbite if you have it in your hand long enough.
Can't go.